Everybody, I'm Vashwar Rouf, and I am a third year PhD student at UC Davis. I and Molly, my fellow researcher, is working on Lorentz force magnetic sensors, and Professor Dave Horsley is our advisor. So let's begin with why we need what is the main application of these magnetic sensors. So our nowadays we want everything in our cell phone, we in our tablets. We want this to have navigational activities so that it can navigate. So there is a e-compass application in iPhone, which is the one of the main target of this magnetic sensor. So to be able to you enable it to use it in smartphones, our magnetic sensors have to be measured at least 200 nanotesla, which gives us a corresponding heading accuracy of the electronic compass of around 1 degree. So and this growing demand of in electronic compasses has given rise to the magnetic sensors. So as you can see, it has risen from virtually nothing in 2008 to there is a projected amount of 540 million units sold in 2013. So what is the current market in magnetic sensors? 95% of the market is currently occupied by the Hall effect sensor. AKM Semiconductor is a leading Hall manufacturer of the Hall effect sensor. Their sensor is actually used in iPhone. So this is a schematic of their sensor. This yellow circle is a flux concentrators, and they have 4 sensors which they can detect 3-axis field, and their minimum resolution is 0.3 microtesla, and they use a duty cycle operation which take 8 samples per second. Another technology that is in use is the MR technology, magnetoresistive sensor. So Honeywell is a company that uses this technology. There is other companies like MEMC and Free Fairchild. They also uses this technology, and Honeywell sensor has a resolution of 500 nanotesla. So why do we care about Lorentz force sensor? Because we already have developed sensor that is used in commercial products. So the main advantage of Lorentz force sensor is like they can be fabricated in the same process that can be used to fabricate gyroscopes and accelerometers. So the main advantage of it, in the same die we can fabricate accelerometer, magnetic sensor, and the gyroscope, and we can easily fabricate in a single chip with inertial measurement unit. So and another advantage of the Lorentz force sensor, like they don't need any special magnetic material like the MR sensors need. They also don't need any flux concentrator like the Hall sensor need, and they are free from hysteresis. So our ultimate goal is to develop a magnetic sensor which can consume like less than 1 milliwatt per axis. We also want our sensors to be as small as possible, because the smaller the sensors are, we can put more in the same die, and it will be much more cost effective in the microfabrication process. And we also want to measure the 3-axis using a single sensor, and our target resolution is 200 nanotesla per root hertz. Again, this is to ensure that the compass has a heading accuracy of 1 degree. So this is the Lorentz force sensors is actually not new. A lot of work has been done in this field from 90s. This is a summary of some of the important sensor. So as you can see, all the previous work, our sensor has the lowest area. This is actually lower than half than our previous work. And our sensor resolution is actually very good, which is compatible with the Hall effect sensors currently in use. And you can see that this sensor, the Kyonarian, they have developed a sensor which has actually very good resolution and very low current. But the problem of this sensor is they have a very complex fabrication process. Their fabrication process is not compatible with fabricating gyroscopes and accelerometer. And to achieve this resolution, they need a very high vacuum. They need a vacuum of around 600 microbar, I think, which is not available in cheap scale in current commercial product. So as you can see, our sensor, this sensor which is fabricated in a standard MEMS process, can achieve a good resolution with a reasonable drive current. So let us see how our sensor works. So on the right hand side we can see a schematic of our sensor. The red line indicates the current flow. So when there is a current flow in this direction, and when there is a magnetic field like perpendicular to the screen, then there will be a Lorentz force and the sensor will move. So, and this is the equivalent circuit diagram. So what we actually do is we flow the current at the natural mechanical frequency of the device. So the main purpose of this is then our motion will be, if we drive the current at the natural frequency, our resulting motion will be amplified by the quality factor of the mechanical structure. And there are these capacitive plates which will detect this motion, and we will use the sensor is connected to a transcapacitance amplifier which will convert this motion into a voltage, and from there we get the sensor output. The important point is this sensor has 2 degrees of freedom. So when the magnetic field is in z-axis perpendicular to the screen, the sensor will move in plane. And let us see when the magnetic field is in x or y-axis, like parallel to the screen, then the sensor will feel a Lorentz force which will move it out of plane. We can see it in this FEM photos. So this is our in plane motion, this is the z-axis field, and this is the out of plane motion which is for x or y-axis field. So in short, we can use a single MEMS structure to detect the field in 2 axes, and our in plane natural frequency is around 50 kilohertz, and the out of plane natural frequency is 124 kilohertz. So let's get a better look at our sensor. So our sensor is based on a MEMS resonator which is 240 by 400 micrometer, and the device MEMS layer is a 10 micrometer thick single crystal silicon layer, and there is this yellow line, this shows the metal layer, this is underneath the structure which is used to detect our out of plane motion, and these are our in plane electrodes to detect the in plane motion. And these sensors are vacuum sealed on a cheap scale, and they have a very modest vacuum, not a good one. So let us go to see the experimental results of our sensor. So these are the frequency response of our sensor. This is the in plane motion and this is the out of plane motion. So our in plane motion, they have a quality factor of 110 and their natural frequency is 40.5 kilohertz, which is in good agreement with the FEM models. And the out of plane motion has a quality factor of 310 and has a natural frequency of 107.4 kilohertz. And the bandwidth of our system is around 180 hertz for both axis field, which is good for uses in smartphone application. And this is the magnetic field sensitivities of our sensor. So for this, we applied a drive power of 2 milliwatt to drive the sensors, and we applied a DC bias of 15 volt. Our sensor has for z-axis field, our sensor has a sensitivity of 3.2 volt per Tesla, and for x or y-axis field, it's 0.92 volt per Tesla. As you can see in this figure, our sensor is very linear up to very close to 1 millitesla. And since our target application is to only measure the earth field is around at best 70 microtesla. So our sensor is actually very suitable for operating in the smartphones. And here we can see the output spectrum of the sensor. So what we did is we applied a 10 hertz AC magnetic field to the sensor, and if you can see, then the 10 hertz 44 microtesla is close to Earth's field. These two tones indicates the applied magnetic field, and you can see that our noise floor corresponds to, like, for z-axis field 285 nanotesla per root hertz, and for x or y-axis field is 344 nanotesla per root hertz. For z-axis field, our sensor is limited by the thermomechanical motion or the Brownian motion of the mechanical structure. So it is as best as we can get. We cannot improve it anymore. And for x or y-axis field, our sensor is limited by the electronic noise from the detection electronics. We implement all our detection electronics on a PC board. So in future, if we can reduce the parasitic capacitance from the PC boards, we can further improve this resolution on the x or y-axis field. So this shows actually the thermomechanical noise for z-axis magnetic field. So what we do is, like, when there is no drive current into the sensor, then the sensor measurement is the Brownian motion. Sensor motion is the Brownian motion of the sensor, and we just take the output, and this is our Brownian noise. So as you can see, it has a peak of 285 nanotesla per root hertz. So, and it has a peak of 285 nanotesla per root hertz. So the way to further improve this resolution is, one way to is, like, we can increase the drive power. If we increase the drive power by only 4 times, the resolution will go down twice, 2 times. That means by 8 milliwatt power we can achieve a resolution of around 140 nanotesla. And the another way to increase improve the resolution is to increase the Q. That means for a better vacuum packaging of our sensor. Even if we can increase the Q by 4 times, we get, at the same power, we get twice the lower noise. So in summary, these are our design parameters of the sensor. So we have a sense capacitance for 98 femtofarad for in-plane motion and a 118 for out-of-plane motion. Our flexure resistance is 98 ohms, and we get a Q of 310 and 110, and our bandwidth is on the order of 180 hertz. And this is our performance summary. Like, with a drive power of 2 milliwatt and the DC bias voltage of 15 volt, we get a spot noise of 344 for x or y axis field and 285 for z axis field. So in summary, we have demonstrated the smallest MEMS magnetic Lorentz force sensor, and our performance is actually very similar to that of Hall effect sensor that are commercially in use. In future, we are planning to design a sensor that can, this sensor, as you can see, can detect only 2-axis field using a single structure. Our goal in future is to design a single sensor which can detect 3-axis field in a single structure. And we also are planning to design an ASIC to reduce the parasitic capacitance, so that our X or Y axis field resolution can be improved further. I'd also like to thank all the members of UCD Mains Lab who have helped me with the sensor design, and thank you very much for your time. If you have any questions, I'm free to answer.